Today we're going to discuss section 3.6, row and column space. Let's say we have a matrix A that's an m by n matrix. That means it has m rows and n columns. Each row is a 1 by n matrix. Because there's n columns, so it's going to have n entries in that row. And each column is m by 1. So it's an m by 1 matrix. And that's because each column is going to have m entries since it has m rows. Now, that being the case, we can think of the rows as elements in R 1 by n, and we can think of the columns as being elements in R m by 1, or you could just say Rm. Since they're elements in these spaces, we can talk about subspaces involving the rows and the columns. And that's what we're going to call a row space and a column space. So for your matrix A, the span of the rows is called the row space of A. And the span of the columns is called the column space of A. Let's look at an example. Let's say that we have this 2 by 3 matrix, 1, 1, 0, 0, 1, 2. I want to know what the row space and the column space of A are. So let's start with the row space. Well, the rows are 1, 1, 0, and 0, 1, 2. What is the span of these two rows? So the span, let's call these rows, let's call it a set. I'm going to call it R for rows. So the span of these rows is a set of all linear combinations of these two vectors. So it's just the span of 1, 1, 0, 0, 1, 2. Now notice that these vectors are linearly independent because there's only two of them and I can't multiply one of these rows by anything to get the other. So these are linearly independent. Put Li for linearly independent. So that means the span of these two rows, and the fact that they're linearly independent, they form a subspace of R 1 by 3. So the row space, we call this the row space of A, which is equal to this span. The row space is a subspace of R 1 by 3. And the row space has dimension 2 because we found two vectors that are linearly independent and span our row space. Okay, let's find the column space. So let's look back at our matrix. We have 1, 0, 1, 1, and 0, 2. So the column space, and some people abbreviate column space as C of A like this. It's equal to the span of these three vectors, 1, 0, 1, 1, 0, 2. And the column space is a subspace of R2. Now remember, R2 has a basis, and the basis consists of two vectors, and here I have three vectors. Now these vectors are not linearly independent. So let's see. We want to find a basis for the column space. What do we notice? Well, if I take one of these and a half of this one and add them together, I'll get this vector, right? So notice that 1 times 1, 0, plus 1 half, 0, 2, that will give me 1, 1, which tells me that this vector is a linear combination of the other two. So let's get rid of it. So the column space is the span of these three vectors, but if I get rid of this, I don't change the span. So this is equal to the span of just 1, 0, 0, 2. Now these two vectors are linearly independent, right? I can't get 0, 2 from this one. So we have two vectors that span the column space. The column space is actually R2 because it's a subspace of R2 that has a basis of two elements, but R2 has a basis of two elements. Any subspace of R2 would have to have less elements in the basis. Also notice that the column space, which is a span of 1, 0, 0, 2, this is the same thing as the span of 1, 0, 0, 1, because this is just a linear combination of that one. So this is R2. And if you want, you can say R2 by 2 times 1, but if we don't put a 1 here, that's okay, because we know we're talking about R2. So we found the column space and the row space of this matrix. Something else you'll see is the range of a matrix A. The range of a matrix is all the solutions to A times X, where X, if A is a M by N matrix, let's say this is M by N, then X belongs to Rn. So this is all the products you can get for any vector in Rn. If you multiply it by the matrix A, that product you're going to get, that belongs to the range. And this is going to be a vector in Rm. So let's talk about this. If we have X in Rn, this matrix A, that's M by N, A times X is the same thing as breaking this matrix into its columns, and there's going to be N of them. Well, X, we can think of X as X1, X2. Remember, it's N by 1 matrix, so all the way to Xn. So I'm actually going to erase this X, and I'm going to put X1, X2 all the way to Xn. And this is equal to A1 times X1 plus A2 X2 all the way to AN Xn. But these guys are matrices, and in fact they're column matrices. And here this is like a scalar. So this is equal to X1 times this matrix, which we're calling A1, plus X2 A2 all the way to Xn AN. So the range, you can see, is just the column space of A, because it's linear combinations of the columns. Here, these x's can be anything in R, because this whole vector x is in Rn. And so we're just taking linear combinations of the columns, which is exactly what the column space is. So it's the span of the columns. So this tells us that the range of A is equal to the column space of A. And that brings me to an interesting point. Let's say you have a system. So the system AX is equal to B. A being an m by n matrix, X being n by 1, and B is an m by 1 matrix. Let's say you have a system like this, and you want to figure out if it's consistent. So this system is consistent if and only if this vector B is in the column space of A. In other words, so think about what we just did a minute ago. What we're looking for is things in the range. We want to know if B is in the range of A. You see how I have written here AX is equal to B. Remember how we figure out if a system is consistent. We put A here and we put B here, and it's consistent if when we figure out the reduced row echelon form, we don't have a row of zeros and then some non-zero number here like a 5. Then it's a if we have this, it's inconsistent. If we have a row of zeros but we also have this as being 0, then it is a consistent system. So inconsistent, non-zero here but lots of zeros here, and consistent as long as that doesn't happen. So we want to know if the system is consistent. So we have A times X is equal to some vector, which means that vector is in the range. And since the range is equal to the column space, which is just multiples of the columns, we're just finding linear combinations of the columns, then we want to see if B is equal to a linear combination of the columns. So if it's equal to a linear combination of the columns, it's in the column space. So as long as B is in the column space, we're going to have a consistent system. So we're going to focus on figuring out the row space and the column space of a matrix. And a good question to ask is, what happens to the row space of A when you perform row operations to A? So let's think about this. So we have this matrix A that's m by n. And we can also write A as just a bunch of rows. So let's say this is A1, A2, all the way to AM. Because it's an m by n matrix. Now I'm going to perform row operations. So what could I do to these rows? Remember that the row space is the span of our rows. So one thing I can do is I can interchange the rows. That's a row operation. But if I interchange the rows and I create a new matrix where I just switch 2 rows, then the row space of this new matrix is going to be the same as A. If I multiply one of the rows by a non-zero number. Am I changing the row space? No, because it's just a multiple of one of the rows. So if I multiplied this row by 2, it would still be in the same row space. What if I added a multiple of one row to another? Well, that would be a linear combination of these rows. I'm not changing the row space. So elementary row operations. Do not change the row space of a matrix. Why is that important? If you put a matrix in reduced row echelon form, its row space is going to be the same as the reduced row echelon form. So if two matrices A and B are row equivalent, then they have the same row space. The next thing I want to tell you is the definition of the rank of a matrix. The rank of the matrix A, which we're going to denote as rank of A like this, this is just equal to the dimension of the row space. In other words, when you find the row space, you count how many vectors are in the basis of the row space, and that number of vectors is equal to the rank. Let's look at an example. What's the rank of this matrix A? 1, 2, 4, negative 1, 3, 1, 2, negative 1, 3. To find the rank, let's find the row space. So we need to find a basis for the row space. Well, our row space is equal to the span of these three rows. 1, 2, 4, negative 1, 3, 1, and 2, negative 1, 3. Are these three vectors a basis for the row space? Well, they obviously span because we said that they're the span of the row space. We need to check if they're linearly independent or not. So to check if they're linearly independent, we put a C1 plus a C2 times this one plus a C3 times this one, set it equal to 0, and solve for C1, C2, and C3. Another option, which is what we just talked about a minute ago, is to put this matrix in reduced row echelon form. If you put the matrix in reduced row echelon form, the row space of it is going to be the same as the row space of A. So let's put the matrix 1, 2, 4, negative 1, 3, 1, 2, negative 1, 3 in reduced row echelon form. Okay, I'm going to add row 1 to row 2. Then subtract 2 times row 1 to row 3. Let's make sure I didn't do anything wrong. I think I forgot to. Let's try that one again. Cross this one out. This is negative 2, negative 4, negative 8. Now add it, and I get 0, negative 5, negative 5. And then you can see that I can get rid of row 3 by adding row 2 to it. I can also divide this row 2 by 5, and then negative 2 row 2 plus row 1. And now I have put this matrix in reduced row echelon form. So you can see that the row space of the reduced row echelon form of A is equal to the span of these two vectors, 1, 0, 2, 0, 1, 1. And this row space is equal to the row space of A. I can get all three of these vectors as linear combinations of these two. For example, 1, 2, 4 would be one of these and two of these. I'd have a 1, I'd have a 2, and then 2 plus 2 is 4. You can do that for each one of these vectors here. So since the row space of A is equal to the row space of the reduced row echelon form of A, then the row space is the span of 1, 0, 2, 0, 1, 1. And notice that these two vectors are linearly independent. Whenever we put a matrix into reduced row echelon form, we're going to get linearly independent vectors. And you can just see it from here. You can't get this vector from this one. And so we have two vectors. These two vectors form a basis for our vector space, the vector space being the row space. Two vectors in B, which tells me that the rank of my matrix, which is equal to the dimension of the row space of A, I'm going to abbreviate it as RS, that is equal to 2.